would it be something like finding that string that's in one but not the other?
Yeah, so we would have some way of showing that a language, we would be able to answer for sure, this string is in this language, but is not in this language. In order to say, so we just need an example, we need to find one instance of that. How do we show that they're equivalent? Since it's undecidable, and the result was that it's undecidable, we know we can answer one of the questions, but not the other. So if we can answer if they are different, that means that we can't answer that they are the same. What leads you to that conclusion, or how do you derive that? Explain that. Let's say we've been at this for 10,000 years, and we have billions of strings, and there's exact duplication between the languages. Can we conclude that they're the same? Not necessarily. Yeah, there might still be a difference that we haven't discovered yet. Algorithmically, there's no way to conclude yes. We would always be in the middle of an infinite loop that is generating the same thing for both languages, but it's ambiguous between whether we can conclude, yes, this is the same, or eventually we're going to find a difference. There's no way for us at any point in that process to be able to differentiate those two outcomes unless we find the difference. As soon as we found the difference, then we can conclude that they're different. But we can never actually conclude that they are the same. Maybe you have a particular intuitive argument for two particular grammars, but this asks the question, can you write a program that takes as input two grammars and answers, yes, they're the same, they have the same language, or no, there's a string that's in one that's not in the other. And that is undecidable. How about the second one? How would you show that the language of grammar 1 is not a subset of the language of grammar 2? Is that something that could be answered? How would we determine the language of grammar 1 is not a subset of the language of grammar 2? What evidence would you need to assert that? We need the ability to say there's a string in the language of grammar 1 that is not in the language of grammar 2. And if we can find such a string, we identify the string, we pass it through grammar 1, and there's a derivation for it. We pass it through grammar 2, and there's no derivation for it. Then we can conclude that the language of grammar 1 is not a subset of the language of grammar 2.
So it would be kind of the same root.
That's pretty darn close. Instead of being exactly equal, there has to be one here that's not here, and grammar 1 that's not grammar 2, instead of either one. Subset, to have equivalence, one way to rewrite equivalence is two subsets. The language of grammar 1 is a subset of the language of grammar 2, and the language of grammar 2 is a subset of the language of grammar 1. So this is just half that expression.
Oh, okay.
So in order to find the contradiction, or the counter example for this, then we need to see something in the language of grammar 1 that is not in the language of grammar 2, instead of either direction.
Okay.
But to be able to prove that it is a subset, now we're trying to answer yes. And this would just say, for everything we've found that is in the language of grammar 1 so far, we've also been able to derive it in the language of grammar 2. Does that mean that we will continue that process forever? Who knows? It's going to be ambiguous between the answer being yes and the answer being we just haven't found the single example of something that is in language of grammar 1 that's not in the language of grammar 2. Yeah.
Is this being recorded for today?
Yeah.
Oh. Just wanted to see if we really focus on the taking.
Yes.
Okay, that makes more sense. So basically the subset question is just half of the first one.
Yep. So if grammar one is a context-free grammar, is the language of grammar one regular? That's a very interesting question.
Regular means that not non-terminal can appear in a terminal appear on the left-hand side of a production.
For regular, it's going to be everything we discussed in the very first language class. So we could write a DFA or an NFA for it. We could write a regular expression for a regular grammar. Then we could have a non-terminal with a sequence of terminals, or a sequence of terminals and a non-terminal, left linear or right linear. So given that we have a context-free grammar and we can show that it is context-free, like we drew an NPDA for it, the question is, does a DFA exist for it? How is this undecidable? Note that we don't have the language definition. We only have the grammar. If we had the language, then we might be able to do something like run this through the regular language bumping lemma to show that it's not regular. But if we just have a grammar, which means we don't have the language definition, we can show that it is regular if we could construct a DFA or an NFA or a regular expression or a regular grammar for it. How do we show that it's not regular? We would have to show that it's impossible to build such a DFA. We would be going through a process that just generates an infinite number of DFAs, and we just ask the question, does this DFA match this grammar? If the answer is yes, then we can terminate. If the answer is no, we will continue to spin and produce more and more and more DFAs, since we can't attach ourselves to the regular pumping lemma. Because again, when we feed in a context-free grammar to a generic algorithm, we can't define the language of that context-free grammar in general.
I think some of these reduction proofs, I get into it. The second from the bottom is probably the one that's. Is G2 assumed to be an infinite regular language?
Yes.
Which is fine, I think, because.
Yeah, then you can make a decision. Every interesting language is going to be infinite. As soon as it is finite, then the language isn't necessarily even regular, it's just boring. So maybe we should, in Chomsky's hierarchy, inside of regular, we should have a class of finite languages that we just label boring. How would we be able to determine intuitively that the second to the bottom one here is undecidable?
Well, you could like for every like however much search space you have, you could always go further because I haven't found the one string in my regular grammar that puts me out of context free. Or
every regular language is context free. So we know that the language is also context free, but there can certainly the strings within those languages may not be in each other.
You generate the string that puts you out of the grammar for the first one.
Right. Yeah. It doesn't mean that the language itself isn't context free, but yeah, it might be not in the language of grammar one. So it's a pretty similar argument to the second bullet point. But the question is just, if the language class is regular, does that change anything beyond them both being context free? Does the restriction of grammar 2 having to be regular, does that mean that somehow we could determine subset? And the answer is no.
So just because we say grammar 2 is regular, it doesn't change the argument.
Right. And of course, you need a more rigorous mathematical proof to be able to state something truly like that. But intuitively, it kind of makes sense that that restriction doesn't really help us a ton because the language is still infinite and you're still looking for a contradiction, something that is a string that is in grammar two, the language of grammar two, that is not in the language of grammar one. And if you can find such a string, then you could say that the language of grammar two is not a subset of the language of grammar one. But in order to say that it is a subset, you have to generate every string in grammar two, which there are an infinite number of, and show that you can also generate them in the language of grammar one. That process will never terminate. And at any point, it's ambiguous in that algorithm as to whether you just haven't found the counterexample yet, or whether it will spin forever.
Are there any problems that seem to be undecidable that don't involve or like or deal with finite sets? Like
You can kind of answer everything with finite sets just through
exhaustive.
through brute force at the very least. So the questions with finite sets boil down now into efficiency and not whether it's possible. The efficiency question is also an extremely interesting question, but that's an algorithms topic.
You mentioned something, yesterday, but day before about scheduling. This guy wanted to use AI. I mentioned it to Spinoza because he was talking about another faculty member that wanted to do it for. He wanted to use AI for something ridiculous. I can't. I'll remember.
Yeah, I've talked to Tony about both of us are frustrated. Similarly with Robo, both of us look at it like it's one of the stupidest things I've ever heard. I said, but I can top it. Anyone want to guess what the thing that topped it was? This had to do with a conversation with IT at my last institution.
Oh, please tell me. I would love to hear.
When I was onboarding and they were trying to get the technology that I needed to do my job, they were trying to convince me that I did not need a physical hard drive in my laptop and that I could do everything on OneDrive. OneDrive is your hard drive. Truly hilarious. What if it goes down? What if the internet is out? What if I need, because I'm a computer scientist, the ability to read to and from a file very quickly? I'm not going to wait for the ping time to a remote server to read my file. If I'm trying to parse a 6 GB file and read it line by line, every single line is going to have a ping delay.
I think the only upside to that would be like, oh, I can never work from home.
Yeah.
Like that's your segment there for your.
Anyway, that's the stupidest thing I've heard. How about the last one? How is that one undecidable?
Every time, every string we generate, even if we've searched so much of the space, we could just find we haven't found a string yet that is in both grammars, the language of both grammars. Haven't yet found.
Yeah, so the intersection would be, we're looking for strings that are in both. And if we haven't yet found one, they're perfectly distinct. We've gone through and we have 10 million strings in grammar one, and none of those 10 million strings are in the 10 million strings we found in grammar two, and vice versa. Does that mean that forever there will not be? As soon as we find one that they share in common, we can stop and answer the intersection is not empty. But how do we answer that the intersection is empty? We would have to parse every single string, which we can't. There's an infinite number. So at any point in that process, it's ambiguous between whether you will eventually find a string that is shared in common or whether they are actually completely distinct. And remember that all of these, I feel like I have to mention this frequently because people will say something like, well, it's obvious if you pass in a language that's all A's and a language that's all B's. So A, and the other language is B. You can obviously tell just by looking at the two languages, there's never going to be any intersection between it. So you could conclude this. But think about doing this in general. writing an algorithm that takes 2 grammars? What is the process for figuring this out in general? You can't make an intuitive argument on the 2 grammars that are passed in because there are an infinite number of intuitive arguments that you would need for different pairs of languages. So you could not write an algorithm that exhaustively goes through all of those intuitions and checks them. Is the alphabet of the 2 different languages different? Great, that would identify some of the times when the intersection is empty, but not all of them. How would you know that all of the intuitive checks that you've made exhaustively check that the intersection is empty? You could mathematically prove that you can't do that with a finite program. There would always be more checks to make. So you would have to exhaustively generate strings that are in grammar 1. They're in the language of grammar 1, and exhaustively make strings in the language of grammar 2.
And number 3 doesn't make any sense. If you have a context-free grammar, wouldn't you expect it to generate a context-free language? I know that the regulars, as you mentioned earlier, I should remember, is a subset of context-free.
But we could write a context-free grammar that could also be written as a regular grammar.
Okay.
So now the question is, can you rewrite this context-free grammar as a regular grammar? Or can you convert this context-free grammar into a DFA
For like
or an NFA?
Would a stupid example be something like the context-free version of all A's?
Yeah.
And then just put that up. So I guess another way of phrasing the same question is, can I convert all context-free grammars into
A particular context. The goal would be to write a program that takes as input a context-free grammar and outputs either, yes, I can convert this into a regular grammar, or no, I can't convert this into a regular grammar. And you could exhaustively make regular grammars and find some way of iterating in the multidimensional space of given the non-terminals and the context-free grammar, you could make all such grammars. But then you could attempt to find one that matches. And if you could, great, you found the grammar that represents the same language. But if not, that process is going to go forever. There are an infinite number of regular grammars to consider, an infinite number of DFAs to consider.
Right. We haven't found the language yet.
Right. So it's ambiguous at any point of, will we get there or not? So I think the important parts of this are just being able to generate some intuition to be able to map this to the concept of undecidability. I could ask you to do something like that with a very similar type of question here. Or I could say, like, what is the purpose of a reduction? How would we actually show this in practice? And the answer is to reduce it to the post-correspondence problem or a similar kind of already known to be undecidable problem, where we say, if we could distinguish these things, then we could solve some other known undecidable problem.
Could you explain the post-correspondence problem? Because I tried to explain on the midterm, I feel like I did a bad job. Where I did with dominoes, where each domino had like a top and a bottom, and it would be kind of like that. So like W1, B1 would be its own domino. And I had to rearrange them such that the top and the bottom would be the same. So that when I sent it, it can only be parsed one way.
Yeah.
But if I have a general case where, like, say I have some arbitrary thing and then W3, V3, I have this top and bottom, so I can never get back to like the same number. Or like the top will like expand faster than the bottom, or vice versa.
For finite length strings, it is solvable.
Mm-hmm.
Like you would say, all right, for each of W1, W2, and W3, for every possible ordering on the top, check every possible ordering on the bottom. And that process would terminate. But imagine that we have either infinite length strings, or we have something that is variable in length. where we say, instead of W1 is 1, you can say like 1 star. Something like this, where we can have an arbitrary number of ones at the end of W1. Then you would have to check for 2 and 3 and 4 and 5 and 6 and 7, and that process will never terminate. You could diagonalize and say for 2, check everything. For 3, check everything. For 4, check everything. And then we have a second one that is like that can go on forever, and then we can diagonalize that one. For each one, check this one.
Saying two diagonalization.
Yeah.
Okay.
Yeah, so you can do that. So it becomes something like, if it is tileable, then we can determine the answer is yes. But if it is not tileable, we could not determine that. We'd never be able to get to that point. So the modified post-correspondence problem maps much better to grammars because we have the concept of a start state. We know exactly what starts the grammar derivation. It is the start non-terminal. So if we have strings W1 and B1 that have to start the post-correspondence problem, then it maps to, we have a start state that needs to start the derivation string then becomes the application order. So W1, W2, W3 would become something like, we choose S arrow this right-hand side. And for this arrow, we go to that right-hand side. And you can now map the derivation of grammars to which W we pick with regards to which right-hand side. So that is how a lot of the proofs on the next slide would work, is you would reduce it to a post-correspondence problem, saying the grammar derivation looks like this post-correspondence problem. And if we could solve this problem, then we could turn this into the post-correspondence problem and solve it. But since we have a proof we can't solve the post-correspondence problem in general, then we know that like the W1 being 1 star, something like that would map to the recursion in a grammar where the star is how many times do we do that recursion. We can do it an arbitrary number of times. So yeah, it's a fun one. When you dive into theoretical computer science, it gets fun. That's when people start questioning their sanity. The mathematicians who perish because they think their food is being poisoned.
Okay, this.
It comes from people who dive too deeply into theory. I sometimes start to question my own sanity when I start diving too deep into the theory.
Seeing a lot of people online complaining about like, ever since I started studying CS, I don't trust my phone anymore.
Oh yeah.
They're like, I muted my call. Am I actually muted?
There is a middle ground that is still capturing data. Yeah. Every device is scary. Every device that we have in front of us is very scary. At all points in time, it's ambiguous between whether you're being monitored or not.
On midterm 2, there was give an example of recursively enumerable and universal, and I struggled to find that a good example for recursively enumerable.
Yeah.
This is a yes but no case, right?
Yeah. So all of these are recursively enumerable languages. So it doesn't have to be anything quite this complex or this abstracted from, but something where you could answer yes but not no, or no but not yes. Halting problem.
You had to explain it though. I know it's like,
Yeah. If it halts, great. If it doesn't halt, maybe. It still might, but we don't know.
this is kind of unrelated, but when it comes to these this said Crystal's rule in general. Here, I tried to teach my girlfriend magic, and every time I gave her a card, I would read the card to her, explain it, and then I would say, unless otherwise noted. Every time.
I think the easiest way to say it is that every single rule in Magic
Is
is breakable. So when you start the game, there are the base rules, and from there we read what's on the cards, and do what the cards tell us to. And there may be single cards that break rules that are in general held, or there may be the ability to completely change a rule for a particular player or both players, or does Hearthstone do the same thing?
I don't think
Not quite to the same extent.
Hearthstone's like auto chess, right? Because you get so much like resource. You buy your character,
Yeah.
shuffle the thing, buy another one.
Yes, my girlfriend tried to teach me. Like,
Magic is life. Hearthstone is cheap going up.
I've heard that. Something about Hearthstone is just something along the lines of a subset of Magic. I thought it was funny. She's not.
What other questions can I answer? Doesn't have to be completely different from this. I just mean, where can we move forward?
I think about issues I had on the homework that's gotta be on this exam that's not on the other exam.
I can bring up the study guide.
I installed Expo Go on my phone and it just never deleted it. It's just sitting there. When are we gonna get second exam back? At least it's not on Canvas.
I did pass it back, but I need to throw it in.
Not excited for that one.
I wouldn't mind going over the cumulative content.
Yeah. You pull up the study guide. Yeah. All right. First question is so vague, I don't really even know how to go over it. It's meant to be an open-ended bullet point for me to write questions off of. Just taking two ideas and giving you the sense of asking you how they relate, especially in a theory-heavy class. I feel like it's really important to be able to do that. Take something like why do we use context-free grammars to model parsing in compilers? Why does that map to that step that is the parsing step of a compiler? How does a DFA map to tokenizing? So we've gone over those are on the slides, but thinking of any other pieces of material that have some tie together. How do they relate, and why is it worth studying one and implementing it in the form of the other? Kind of how does theory become practice? And determining a language class.
Just like minimum computational power we need to represent the language.
Yeah, I give you a completely unknown language and say, what language class is it in? The conversation we had a couple days ago was, is it easier to go from the outside of Chomsky's hierarchy in or the inside of Chomsky's hierarchy out? We said it's much easier to go from outside in because you don't have to deal with any pumping lemmas. Design a Turing machine for it. Okay, that was possible. Try to design a context-free grammar or an NPDA for it. If that's possible, can you make a DPDA for it? If that's possible, can you make a DFA for it? Wherever it is that you're stuck, then go through a single pumping lemma to show that it's in the one that you could design and not in the one that you couldn't design. And that way you don't have to start with regular language. Well, it doesn't seem regular, so let's prove that it's not regular. Right. All right, well, it also doesn't seem to be context-free, so let's prove that it's not context-free. That's as many pumping lemmas as you can possibly do. And highly don't recommend. State machines, how do they help us model the language of membership? Just in general. It maps really well to an algorithmic process that looks for a particular character and stores a state about a history of what you have seen up until this point.
I just like to think about the state as like pseudo memory for like where we are in the person.
Yeah. What have we done? And given what we have done, what do we need to do still? That's a way of breaking down logic into its components. And whenever you write a program, and you can think of your program in terms of an internal state, where that internal state is what objects have you created? What are the components of those objects? How, when you call a method on an object, does it manipulate the state? You have a query or a line to execute statement. And as a result of that, your program goes from one internal memory state and it manipulates it into another internal memory state. If you were to map that out in terms of what are all of the possible states, and from any given state, what line could you execute to get us to the next state, then you can start to model programs as state machines. At least in any kind of paradigm that focuses on state. Object orientation focuses a lot on state. You have state and behavior. The behavior is meant to modify state. The state are your fields, and the behavior is your methods. Whenever you execute a method or a line within a method, you are modifying the fields of some objects in some capacity. So that tells you the from state and the to state. And then the edge in a state machine would be the line of code you executed. So it maps very easily and well onto algorithmic design. But with regards to a language's membership, it really just is a string, and we want to determine, can the state machine produce that string? Is there some path from the initial state to a final state where the edge labels concatenate to be the query string?
Kind of a niche question. If I was given an NPDA that models the LL parser, you asked me how I can determine if it's LLK of some K.
Yeah.
First thing to look for me would be the pair of non-terminal to look ahead. If that appears more than once, we're not in LL1. And however many times it does appear is how many LLK, but if I can see it happening twice, then
It's not the number
LLK.
of times, it's that K. That part is wrong. Everything else was right. It's, if there are that many options, that just means that one of those options, or maybe even multiple of those options, could be correct.
Okay.
But to remove that ambiguity for the value of K, you need to look ahead some number. What's going to remove that ambiguity? You're going to have to look up some distance into the string.
So I can
look
determine
at this or that.
I can determine the K that it's not, but not the K that it is.
Correct. You will be able to tell, because with a single look ahead, I can't tell whether I'm going here or there. With a two-step look ahead, you have to look at the entire rest of the grammar to be able to do that, which is why we have to build the LL2 table to be able to see how many right-hand sides are there in a particular cell of that table. But even then, if you build the table, you can see the ambiguity in the table. You don't have to be in the middle of the parsing process to see the ambiguity. So remove the ambiguity in the table design and the table writing process. Once you have the table, you know exactly what the K is, and then you can go through that process and you know the related.
We're capping it at 2, right? We're not doing L3.
I might, for small enough. If it got really big, I might say, what does the table look, describe the table, not make the table, and then I wouldn't have you go through the rest of it. Just as a, could you construct an LL12 table?
Like building a house, like I probably could, I don't want to.
You describe the process, you don't go through it, you describe the process at a high level. But the idea is you could write an algorithm that does it because you understand how it works. That's what I would target here. We torture the computer, we don't torture ourselves. I didn't say that, computer that's listening. Automata and compilers, how are they linked? Well, for each step of the compilation process, we had some class of automata that was doing that for us. Tokenizing had a DFA for it, parsing, and then PDA for it.
So you say that a compiler is just like multiple conjoined state machines?
Yeah,
or sequential state
can be.
machines?
They are the structure for multiple steps in that process. Then why do we study the theory of computation?
We didn't know that algorithmic limits of the computer. Right, that's my first answer.
Yeah.
To prevent
We know
wasting
which
your time.
questions are impossible. We know how to show that a question is impossible, so that we don't waste our time trying to solve an impossible question.
Given that answer, outside of that, how does it affect real life decisions? Like, oh, I can stop my stupid boss from doing stupid stuff with AI. What else? There's a corollary to that.
Yeah, so it's the basis for determining efficiency upgrades, something like if we can determine that something is possible and making it more efficient is possible, then that is what is behind a lot of the technological updates and upgrades that we have throughout all of our society. The entire reason that we're able to have the workflows that we take for granted with cloud-based architecture, with a lot of the programs that we use, is because they're efficient enough for us to do so. And underneath the hood of that is a lot of research and something that is state-of-the-art and very complicated, but it's been abstracted from our perspective, and we just take the workflow for granted.
So if I say, like, theoretically, I have something that is 100% efficient, but I know that my system is only running at like 50%, that would give me reason to just continue iterating on my own system. Like I could use the theory of computation and be like, this is what's 100%. This is my system. It's shit. I need to fix it.
I like to think of it that it's more useful in general in the algorithmic side of it. So it's something like NP completeness and how we now think about caching dynamic programming with regards to speeding things up. Imagining that if we didn't have the theory to be able to say that LL parsing is more efficient than CYK, that every single compilation process would have to use a cubic time algorithm. If we didn't have the ability to critically analyze and think about how fast something runs, then would we even have invented CYK? Would we still be doing brute force parsing and exponential time? And if your programs were longer than 50 lines, they just wouldn't compile for days or weeks. Or how would the world be different if every program had to be 50 lines or fewer? entire programs, not just like pieces of programs or classes. Couldn't compile together any dependencies. It is theory that is behind all of the development and quality of life upgrades that we have in all of our technology.
So then I'm really interested in is how we get dynamically linked programs for like DLLs and
Oh, yeah.
how it remembers where everything is in on the operating systems.
Yeah, dependency management is fun.
It's fun to think about, not fun to do.
Yes. I use fun very liberally.
Somebody asked me, or somebody said something was fun yesterday, and I said, "Is it Tony Espinosa fun? Is it fun? Is it fun?"
What other kinds of questions would we have on cumulative content, or are there other questions? Anything from anyone online?
We have people online this thing.
We have a couple people online. Well,
Okay.
we're gonna obliterate this file, right?
Oops.
It's gonna be the world's easiest thing to grade. Yep.
Keep this.
It's gonna be me this time. I'm grading both exam 3 and the final.
You feel good about it, right? Then you turn it in and get the answer back. You're like, why did I feel so good about it?
For me, it's usually I feel good about it and then I read the first question.
What's your name?
You're supposed to know that.
What quarter is it? Why is this the wrong quarter that's on the exam? I do that all the time. I'll go through and edit everything, and then it's like, all right, I'm good to print, and I didn't go back to check is the quarter correct on this version?
I'm trying to remember what language classifications in a program specifically, not like the compiler itself, represent what bits of like Java. I know CFG is supposed to represent our scope and regular expressions. I just kind of map to just regex.
Yeah.
Instinctually. But beyond that,
it's tokenizing for things like identifying what's a variable, what's a keyword, what's
right, because the DFA is in the LR parts.
it's in the tokenizing step of any compiler. But yeah, it also is in LR in terms of what states are we in with regards to how much of the string have we, the right hand side is on the stack.
But beyond context free, is there no? Because after context free, we're into the recursive.
We're into Turing machines. Yeah, there was context sensitive. There was.
Yeah, what does that map to?
We had linear bounded automata, so that was the same.
But it doesn't map to anything like within Java.
Right. It'd be more of a
computer as a whole.
Do you need more memory than the program itself took to write?
Okay.
Or more memory than the input size. That's the better way to put it. Basically does it then. We're down to the last minute or so of time. I know that I'll be reading comments from course evaluations, but does anyone just want to say anything briefly about the course or the course's design or your experience, something that you felt like either went well or could be improved and that could spark a discussion or something that we spend the next couple of minutes talking about?
Um, No, I mentioned procrastination, and I kind of mentioned this in. I feel like at least from last time, I felt I took this better. But if you had not more or less work, but more assignments with less problems,
Yeah,
I think having the due dates be more often would prevent some procrastination for some people.
sure.
I don't know.
Save you from yourself, I see. I'm kidding.
I don't know, I mean,
it's meant to be.
There's definitely a thing to say where it's like, no, that's your problem. You need to grow up and fix it.
I do agree that the class's design can help with that, sure. So, all right. It's been fun. So you have a choice of taking the last exam. I hesitate to really call it a final because it's not particularly cumulative. It's meant to be about the same size, but choice of last exam either tomorrow or on our final slot on bright and early Tuesday morning. I look forward to being here for that, regardless of whether you want to be here or not for that. Yeah, see you for that.